Hi and welcome to this tutorial on the Group 7 halogens. In the previous tutorial, we had a look at the uses of Group 2 elements and their compounds in industry and in medicine too. Here we're going to be looking at Group 7, so I'm going to introduce the halogens and also talk about their trends. So we know the Group 7, they're known as halogens, and we're mostly going to be focusing on the first four in the list, so fluorine, chlorine, bromine, and iodine. So of course they're all non-metals and they exist as diatomic molecules, so two atoms joined together by a single covalent bond. And as you move down the group, the boiling point of the elements is increasing. So fluorine boiled a long time ago. It had a very low boiling point, so it's going to be gaseous at room temperature and pressure, as is chlorine. But as we move down, we're going to come across bromine, which is a liquid at room temperature, then iodine, that's a solid. Okay, and the reason for this is because they are simple molecular in their structures. So the only thing that's going to affect their melting and boiling point is the London forces. So imagine if I've got a sample of fluorine in a bag, there is going to be fluorines reacting with other diatomic fluorines nearby, and there's going to be those intermolecular forces. That is the only thing they need to be overcome in order for that compound to boil, for example. So as we move down the group, we are increasing the number of electrons. So bromine, Br2, has got a lot more electrons than F2. And we know from previous tutorials that the more electrons you have, the stronger the London or the van der Waals forces. Therefore, the more energy required to overcome and break those forces. Therefore, the higher the melting and the boiling point. And that's accounts of their physical state. So like I said, fluorine and chlorine are gaseous, and as we move down, they go to solid with iodine. And we know that halogens are in group 7, so they've got 7 electrons in their outer shell, and their configuration, without the numbers, is going to be S2, P5. So we're trying to get that final electron to fill that P shell. And they're really, really reactive because they only need to gain one more electron to get that full outer shell to receive that stable configuration of a noble gas. So you should really know and learn by heart the main properties of the first 4 halogens. So these are some bits of information that people often neglect. So what's their colour at room temperature and pressure, and what's their physical state? And here's our electron configurations. Like I said, at the end, we're always going to have S2P5. S2P5. So we're now going to discuss the trends in the melting points or the trends in general as we move down in our halogens. So what happens to the boiling point as we move down group 7? Well, we just talked about it. So the boiling point increases as we move down group 7. So fluorine, it boiled a long time ago, hence it's a gas at room temperature and pressure. It has a very low boiling point, whereas as we move down, it gets higher and higher and higher. And a bit more detail on this is we're talking about the intermolecular forces, not intra, that's the single covalent bond, the inter, think international, the interaction between different countries, the interaction between different molecules of fluorine. So here is an intermolecular bond. This red dot here, it's not covalent, and it's transient, it's dynamic, it's forever making, breaking, and breaking. So we can only get London or van der Waals forces with simple molecular structures where both atoms are the same, because those electrons are held perfectly in the center, so we have not got a dipole, and we don't have permanent dipole-dipole forces. So we've just got simple London forces, and iodine is a much larger molecule with much more electrons than fluorine. Therefore, the dipole that it's able to induce in the neighboring molecule is more dramatic, it's increased, and therefore the strength of this intermolecular force is greater and requires more energy to overcome, hence the higher melting and boiling point. So if we actually compare them, the boiling point of fluorine is minus 118 degrees Celsius. The boiling point of iodine is 184 degrees Celsius. So although it might seem like a bit of a small difference, it is dramatic when it's happening en masse with billions of molecules. So the increase in the boiling point as we move down is linked, as we said, to van der Waals or London forces. So increasing the strength of those forces because we've got a large amount of electrons in the diatomic molecules towards the bottom. And this also accounts for the increase in melting points and the decrease in volatility as we move down. Let's think about electronegativity as well. So if in my head I've got my periodic table, I know that electronegativity increases as we move into the top right-hand corner, so it's diagonal. So I know that electronegativity decreases as we go down or increases as we go up. Depends on which way you want to say it. So electronegativity decreases as we move down. So all of our halogens vary in terms of their electronegativity. It's an attribute that's given to them. And we know that fluorine is the most electronegative element in the whole periodic table. And it's certainly the most electronegative element in group 7. So as you move down the group, the atomic radius of the elements is going to increase. And there is an increase in the shielding effect. And this means there's a reduced attraction between the atoms. Okay, so therefore, that's why we get that decrease in electronegativity as we move down. And you can see that here, as we're moving down the group, we're getting that increase. And it's very dramatic when you see it depicted like this. There is a very big difference in the amount of shielding for iodine and fluorine. This is a diagram depicting the decrease in the polarity between the carbon-halogen bond as we move down the group. So fluorine is exceptionally electronegative. So you can see the pair of electrons held between the carbon-fluorine bond is held very closely to the fluorine. So this dipole, I've written both of these dipoles as delta positive and delta negative, very big to show that it's a powerful dipole. And as we move down and down and down, we can see the electrons are held less and less closely to the halogen, because as we go down the group, the halogen gets less and less electronegative. So in terms of a tug of war, it's not winning it as much each time. So you see these electrons moving in and into the center to the point where there's not that much of a difference at all really between the carbon and iodine. There's enough of a difference, but in comparison to the top, there isn't. So the covalent bond that holds the two atoms together in the diatomic halogen is relatively weak, and it can be pretty easily broken. So that accounts for the relatively high reactivity of the halogens. And the bond energies of the diatomic molecules as we move down group 7 is going to decrease. So it's easier to break that bond at the bottom of the group 7 than it is at the top. And we can explain that by the fact that the atomic radius is increasing as we move down the group. We've got that shielding increasing, and the distance between the atomic nuclei and the shared pair of electrons in that bond is going to increase. So with that greater distance, that's going to weaken the attraction, and it's going to weaken that bond. And the longer that bond is, the weaker the bond is and the easier it is to overcome. Of course, halogens are non-polar because the electrons in the covalent bond are held perfectly in the middle because both the atoms are the same, they've got the same electronegativity. It's like having a tug of war with the same person on both sides. Halogens are poorly soluble in water, so they're unlikely to dissolve, and they dissolve pretty well in organic solvents. So water is polar, like dissolves like. So water likes to dissolve polar compounds, but halogens are non-polar. That's why they don't dissolve very well. Organic solvents are non-polar, and halogens are non-polar, like dissolves like, so they much more readily dissolve. And there are some characteristic colours that you need to learn. So if we have chlorine, bromine, and iodine. And of course, chlorine's going to be Cl2, bromine's going to be Br2, and iodine's going to be I2. So they're poorly soluble, but they are soluble in water. So chlorine will be colourless. Check your specification. If you are an OCR, they like you to say a very pale green. But I know that this tutorial is across all specifications, so double check that. Double check these colours. So look at past paper questions. What were the answers that were credited as correct? They can be very fussy. Yellow, orange, and in iodine, it's brown. Now, you may recognise this from medicine. So before someone does surgery, if you're watching any programs to do with medicine, sometimes they will put iodine as a disinfectant over the body, and you will see it's brown. It's aqueous iodine, of course, in that case. And then we've got organic solvents, so like cyclohexane. Organic solvent. So chlorine, again, check the colour, but sometimes considered colourless. It's going to be orange-red, the bromine, in organic solvent. And interestingly, iodine's a very different colour. So it's pink/violet. You need to learn these colours.